Hello everyone. So today we're going to talk through three different types of radioactive particles: alpha, beta, and gamma particles. And we're also going to talk through how the Geiger-Müller tube works in a little bit more detail. So the first particle we'll talk about is the alpha particle. Alpha is the first letter of the Greek alphabet. So we will generally use that symbol alpha to describe alpha particles. We know the alpha particles are made up of a pair of protons, so two positive particles, and a pair of neutrons, two neutral particles. This means that it has an overall positive charge of +2, and it's got an overall mass of 4. Now, anybody who's already done some diagrams of atoms might recognize this as being a helium nucleus. So all we need to turn this into a full helium atom is 2 electrons. But the distinguishing feature here is that it actually doesn't have any electrons, so it's not an atom, it's an alpha particle. Now, when a larger particle or a larger nucleus emits an alpha particle, we have to realize that it's going to be emitting 2 protons, because those protons have to come from somewhere, and 2 neutrons. So its number of protons will decrease by 2, or its atomic number, and its mass number will decrease by 4 because it's losing 4 particles overall. So a common question that we can be asked is to describe the alpha decay of uranium-235 and to write it out in an equation form. So first of all, we really have to realize what this means. There's going to be uranium-235 atom, and it's going to emit an alpha particle. As long as we can figure out what a uranium-235 atom is comprised of, and we remember what an alpha particle is comprised of, then this shouldn't be too difficult. So let's first of all look at what uranium-235 is comprised of. If we go to our periodic table and we look up uranium, we will see that it has an atomic number of 92. So we'll write down its atomic number next to it, 92. Now in the periodic table, the mass number for uranium is given as 238. So we're not going to write down 238 for its mass. We're being told that they're using uranium-235, which is an isotope of uranium, meaning it has a slightly different mass. So we're going to use 235 for the atomic mass. Just to recap what these numbers mean, 92, the atomic number, is how many protons are in a uranium nucleus, and 235, the mass number, is the combined number of protons and neutrons in that nucleus. So in this case, that will be comprised of 92 protons and then 143 neutrons to bring it up to a total of 235. Now, if we look at what's going to happen during alpha decay, a reaction is going to take place. So we have an arrow going one way to denote that reaction. Our uranium atom is going to lose 2 protons because it's giving off 2 protons as alpha particle. So the atomic number of our new nucleus is going to decrease by 2 because those 2 protons are being lost. And the total number of particles of the nucleus being lost, 4, is going to be subtracted from the mass number. So 235 take away 4 is going to give us 231. So we'll end up with a new nucleus that has an atomic number of 90 and a mass number of 231. Now it might be tempting to say that this new nucleus is still a uranium nucleus, but it's not, because it's after losing some protons. So with a different atomic number, it actually changes to a different element. So again, we'll just consult our periodic table, and we will see that the new element that has an atomic number of 90 is thorium, Th. So our uranium changes to thorium, but an alpha particle is also produced. Now, when we're writing it into the equation, we don't write it as an alpha particle. We write it in as a helium nucleus. That's why it's important to remember that an alpha particle basically is just a helium nucleus. So our alpha particle, which is a helium nucleus, same thing, has 2 protons and 4 total particles in the nucleus. So it's going to be written as an atomic number of 2 and a mass number of 4. So that's the alpha decay of uranium-235 done now. Now, I think a pretty common problem that people come across is when they're looking up the periodic table in their log tables. The periodic table is on page 79. But this actually doesn't include a lot of the elements that are used for radioactive decay equations. So it's just important to be aware that they also show some of the other elements on page 82. So that's another good place to look if you don't see the element you're looking for. Uranium, for example, is on page 82 because the version on page 79 is just a bit simplified and it doesn't include some of the heavier elements. Now, 2 other things to say about our alpha particles. Because they are so big, they do not manage to travel very far. So they have what we call a low penetrating power. This means that if they're released into air, they will generally only travel about 2 or 3 centimeters, and they won't get much further than that. It also means that if you wanted to stop some alpha particles, you could do that using, say, a thin sheet of paper or something. Now, that might make you think that they're very safe to be around, but there is also another factor here that even though alpha particles cannot get very far, they're very easy to protect yourself from. They do have a very high ionizing ability, which means that they can cause atoms to gain or lose electrons and alter their charge as a result, which is bad for your cells because it can kill your cells or it can cause cancer. So even though your skin will probably be able to stop alpha particles, definitely do not want to ingest anything that is emitting alpha particles. Beta particles, the second letter on the Greek alphabet, are next on the list. The symbol for beta is just the Greek letter beta. It's like a capital B with like a little tail coming off the end. Now, believe it or not, you're probably pretty familiar with beta particles by now. Beta particles are just another word for electrons. But they're called beta particles when they're emitted from the nucleus of an atom. So they're radiated basically. But in terms of their structure, they're no different at all to electrons. Now, what might be confusing to some people is the fact that electrons can be emitted by the nucleus because it is nuclear radiation. I'm sure we're all up to speed at this stage about the fact that there is only protons and neutrons making up a nucleus, so no electrons in there. But the reason it comes about is because of the breakdown of a neutron. So we have loads of neutrons inside a nucleus. They have an atomic number of 0 and a mass number of 1. So no protons in a neutron, but they do have mass of 1. Now, the type of thing that happens to the neutron is it splits up into 2 different particles. It splits up into a positively charged proton and it splits up into a negatively charged electron. So there is a certain amount of conservation of charge. The charge is neutral beforehand, and then afterwards we end up with a positive proton and a negative electron, which cancel each other out. So just in order to fill in there what the atomic number and mass number of each of those particles is, a proton has a proton in it, so it's got a atomic number of 1. It's got 1 particle in it, so we say it's got a mass number of 1. An electron is interesting. It doesn't have any protons in it, but because it's got the opposite charge, we give it an atomic number of -1. And the electron will have a mass of 0. Now I know you can look up your log tables and find the mass of an electron, and you could give it a very specific number that isn't 0. But compared to the mass of a neutron or a proton, the mass of the electron is negligible. So we just say for these purposes that its mass is 0 because it would be a tiny fraction of what these are, our atomic mass unit that we're counting as 1. So we can have a look at another nuclear equation for this one, and we're going to look at the beta decay of carbon-14. So we'll look at carbon in our periodic table. We will see that it has a atomic number of 6. In the periodic table it has a mass number of 12, but again they're giving us a particular isotope to work with here, so we're going to use 14 as our mass number. So our carbon is going to undergo nuclear disintegration. So we're going to just show an arrow to show that's a one-way process. It's going from this and it's ending up as what we're going to write over here. So now if we think about what's going to happen to this carbon atom, it's going to produce a new proton. So whatever we end up with is actually going to have an extra proton here in the center, or in its nucleus. It is losing a neutron because the neutron is breaking down, but it's gaining a proton. Both of those have approximately the same mass, so its mass number is going to be 14. Next we'll just check our log tables to see what element has a atomic number of 7. So next to carbon we have nitrogen with an atomic number of 7. So next we have to remember that there's also a beta particle being emitted here. Now we don't use the symbol beta generally, but we will write in the fact that it's an electron. So again, it is important to remember that a beta particle is just an electron, which is going to have a atomic number of -1 because it's the opposite of a proton. It's going to have a mass of 0. So just like with the alpha radiation or alpha particle decay, it has the same total mass number before and afterwards. So there's 14 mass before, 14 mass afterwards. And the charge also is conserved before and after the equation. Before the equation it's got a charge of +6. After the equation it's got a charge of 6 if we take 7 and subtract our 1. So both the mass and the charge are conserved before and after for alpha and beta. Now if we look at the characteristics of beta particles in terms of how dangerous they are, they have a medium penetrative ability, which means they're somewhere between alpha particles and gamma particles. Beta particles can generally be stopped by about 30 centimeters of air. They won't make much further than that. Or alternatively, a thin sheet of any kind of metal, even a lighter metal like aluminium, should be able to stop beta particles with a thin aluminium sheet. In terms of their ionizing ability, they're again somewhere between alpha particles and gamma particles. So the third and final type of radiation is gamma rays. The symbol for gamma that we often use is something like this. It's kind of like a Y shape. So it'll look like this. Sometimes it's drawn like that, or sometimes it's drawn going down first. Now I'm sure we've all heard of the term gamma radiation before, from when we studied our electromagnetic spectrum. Gamma rays are of course one of the types of electromagnetic radiation, and they have the highest frequency and therefore the highest energy compared to any of the other types. So in terms of why and how gamma radiation is emitted from a nucleus, we have to just look at what the structure of a nucleus is like. So we have some red protons here, and we have some blue neutrons, and these are all kind of held together by the strong nuclear force. Now sometimes what can happen is the way that they're held together, or their arrangement, you can see it's here, is kind of random. Sometimes that can change slightly, and if it changes slightly to a arrangement that requires less energy to keep it together, then the excess energy will just be emitted out from the nucleus. So we'll show that in green now. The extra energy just leaves the nucleus, again just due to a slight rearrangement that requires less energy to hold them together. So that raw energy is emitted as a beam of electromagnetic radiation, or we could even say a beam of photons if we wanted to call it a particular particle. But because the radiation is so high, high in energy and high in frequency, we call that gamma radiation, because again that's the highest on the electromagnetic spectrum for frequency. And because photons have such a tiny mass, um, then really there is no equation that we need to turn off for this, because the mass is pretty much unchanged in here, as is the amount of protons. So no net change overall, so no equation that we need to learn how to do. So as far as the characteristics of gamma radiation has a very high penetrative ability. This means that it can travel through pretty much any material, and the only thing that's going to stop it is very dense. So on the course we learned that the thing that will stop it is thick lead. So you'll see that similar to the way that X-rays are stopped by thick lead. Its other characteristic that we need to be aware of is its ionizing ability. For gamma rays, the ionizing ability is actually quite low compared to the other two. So lower than alpha and lower than beta particles. Traditionally, when we hear of gamma radiation, we kind of think that it's the most dangerous one, and we see it turning Bruce Banner into the Hulk and everything. So I'm not saying that gamma radiation isn't actually dangerous. It absolutely is, particularly because its high penetrative ability lets it enter our bodies quite easily. Even though it does have low ionizing ability, it's a lot like other things in that the dose makes the poison. So if there's enough of it present and it is able to penetrate into your body, then it obviously can cause some health problems and different things like that. So the last thing we'll look on this video is the Geiger Müller tube, or sometimes called a Geiger counter. Now this is used to detect radiation, so it'll be used by people working in environments where there could be some possible radiation that they would need to be aware of. So if the Geiger-Müller tube starts giving higher readings, then they maybe need to limit their time in that environment, or they might need to leave immediately. So I'm going to draw you the diagram of the Geiger-Müller tube, and I'm going to talk to you about each of the different individual things that I'm drawing as I go along. So a Geiger-Müller tube, first and foremost, looks like a tube. It has a kind of a pin that runs down the center, and it has a thin window on one end that the radiation can enter through. The material that's used to make this window is called mica, but again, the most important thing about that window is that it's really thin, so it'll keep this separate from the outside world. No gas can get in or out, but it will allow particles to travel through it, even things like alpha particles, which are generally quite bad at passing through stuff because of their low penetrative ability. Now the tube is filled with something that we want to act as an insulator. So normally what they will fill it with is a low pressure gas, the most commonly used of which is argon. Now the next step involves connecting up the central pin to turn it into an anode. So it's going to be connected to the positive terminal of a power supply, and the outside of the tube is going to be connected up to the negative terminal of a power supply. So at this point our central pin has become an anode, and the outside of the tube has become a cathode, because a charge will build up on each of them. Now at this point current will try and flow through the circuit, but it can't, because it can't get from the negatively charged tube across to the positively charged interior. So current can't flow between these two under normal circumstances, because the argon gas acts as an insulator. The exception to this is when radiation passes through our thin mica window here. Radiation, as we know, has an ionizing ability, so it'll create ions, positive or negative. Positive ions are going to go towards the negative cathode, and negative ions are going to go towards the positive anode. So if a piece of ionizing radiation comes in here, alpha, beta or gamma, it will cause a brief flow of current. Now we have another component in this circuit, and this component, what it does is it amplifies that electrical signal, and then it will count it in some way. So some Geiger-Müller tubes will be connected up to something that will give a number, that's called a rate meter, and some of them will be connected up to a speaker so that it gives a click whenever a current flows briefly. Anybody who's ever played the Fallout series of video games will probably be familiar with the Geiger Müller tube. There's always one in the background, and whenever there's increased radiation in your surroundings, you start hearing a increasingly more frequent clicking noise. So that's what a Geiger Müller tube would sound like. So what is really important for the Geiger Müller tube is that we know this diagram with all of the different labels attached to it, and that we can also explain in a very clear step-by-step way what's happening in this setup, so that initially no current can flow because of the gas. Then ionizing radiation enters, creates ions, which then cause a brief flow of current, and this is then picked up by the amplifier and counter, or amplifier and speaker, depending on what the case may be.